Yeah, in my previous class, I introduced the term Calixarenes. So, we will take a look at Calixarenes in some more details. Okay. Calixarenes. So, Calixarenes are a series of macrocyclic phenols. Okay. Macrocyclic phenols. Now, when unsubstituted phenols are reacted with formaldehyde, this is unsubstituted phenols. It reacts with formaldehyde at high temperature. Okay. Then it gives a resinous material called bakelite. Bakelite all of us know pretty well. Okay. Commercially it is quite useful. So, it gives you bakelite. This was discovered in around 1870, long time ago. It took almost a century to find out that if people were interested, and so they found that they tried to do para substituted phenols, specifically tertiary butyl substituted phenols. If we react with formaldehyde, in some neutral solvent, they use linseed oil as the solvent. Linseed oil at 200 degrees Celsius and for several hours. If you reflux it, you get a mixture of calixarenes, mixture of products that turned out to be very different from resinous bakelite, and it turned out that this mixture of products is nothing but a mixture of calixarenes. Okay. And this calixarenes name was coined by two persons, one of them is Indian also, Gutse and Muthu Krishnan. They gave the name Calixarenes. Calix means vase in Greek. Calix means vase because it was found that specially 4 calixarenes and 5 calixarenes. I will come to that, what is the meaning of 4 and 5. They have similar, they have a 3-dimensional structure, this is a non-planar and very much resembles like a flower vase. So, let me write the structure of 4 calixarenes. I am writing, you have to give me some time because it is quite difficult to draw this structure. OH, this is 1, OH, this is 2, then this is 3 and the other one is inside, you see. It's kind of difficult to write, but still I will try. Okay, I do not know whether you understood that, but this is what I have written is called Calixarenes. Okay, so this is Calixarenes and actually my drawing is not anywhere near, it is like a cone shape. Let me draw a cartoon now, if you allow me. Okay, is like that. OH, 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 and then you have tertiary butyl group. So, this is a cartoon variety of Calixarenes and this part is looks like a flower vase. Here is a flower vase. I will draw the flower vase also. Okay, is a flower vase. So, there is a similarity in this structure whatever there, and this description of non-planar structure is very true for Calixarenes and Calix5-arene. And I must tell you that Calixarene is an important milestone in the development of supramolecular chemistry, and this caught the imagination of chemists. Okay, as soon as its structure was elucidated, is non-planar structure. Okay. Now, other higher Calixarenes, okay, higher Calixarenes means beyond 5, and as we go higher and higher, say Calix10-arene or something like that, then or even higher than 5 Calix5-arene, in the crystalline state they can be planar. Okay. So, this planarity will increase as we go to the higher and higher homologue. So, that is one aspect. Now, second aspect is, okay, I will also describe this. This is called upper rim. This is upper rim. Let me write upper rim, upper rim, upper rim, lower rim, lower rim. Okay. So, upper rim and lower rim, and this is the hydrophobic. So, this part upper rim and this aromatic arene, this part is hydrophobic in nature and it can accept hydrophobic guests, and this is this lower rim is hydrophilic in nature. Obviously, you can see OH groups, there are 4. So, this lower rim can accept metal ion, can bind metal ion. Okay. So, is a hydrophobic and hydrophilic is characteristic of this particular molecule. These molecules are absolutely fascinating. Okay. And why it is calyx 4 arene? 4 arene means 4 benzene ring, that is why it is calyx 4 arene. When I talk about calyx 6 arenes, then you know that there are 6 aromatic groups there, okay, like this. All right. Now, what caught the imagination of chemists for this kind of molecules? Let me show you with an example. Cartoon variety. To make this, draw this picture is beyond me is very difficult. You cannot do these 3D structures in hand, okay, but we can make these cartoons. We can make cartoons like this. Okay. All right. So, this particular calyx 4 arene, they are these compounds, all arenes are conformationally very labile at room temperature. All right, and that can be monitored by NMR spectroscopy also. So, this is a calyx 4 arene. I have not written the lower rims are not there, substituted by hydrogens. So, now it can exist like this, is a cone, complete cone, and there after that it can be like this, can be like this. Okay. No, not this, this is not there. So, let me draw. This is one, this is the other one, and then this one, and we come here. Okay. This one is there. So, one of the group, one of these can invert and come down like this. Okay. They can easily come like that, and that happens at room temperature. So, that is why it is very Interesting. It can be that, or it can be what is called 1-2 alternate. I am writing 1-2 alternate. Let me write. Let me write. Okay. Or R, and then R, R. This is called 1-2 alternate. 1-2 alternate. And then I will write 1-3 alternate also. Let us see whether I could do it properly. Does not look very nice, does it? Let me write it. Okay. Okay, all right. Just try to make it better. Okay. Sort of this. Let me write now. Okay. Now, unfortunately, well, it is all right. R, R, R and R. Okay. Good enough. All right. This is known as 1-3 alternate. 1-3 alternate. I will show you. If this is 1, then this one is 2, 3 and 4. So, 1-3 alternate means this and this are inverted and other 2 remains as it is. 1-2 alternate means the 2 consecutive ones, 1 and 2, these are inverted, the other 2 remains same. Okay? And in the this case, only one of them gets inverted, and finally, the original one, all 4 are uninverted. So, this kind of movement of these aromatic groups from here and there, from up and down, that can take place at room temperature very readily, and so this caught people's imagination that with these kind of molecules, it is possible to make molecular machines perhaps, And so, people jumped into this and large number of publications, large amount of results were accumulated. Okay. Now, I will tell you, but today right now I am not going to show you what are these uses and people have used, but I will show the characteristics. Okay. All right. The okay. Let me again draw this. The conic cone form. Oh, I must tell you that I have made only 4 conformations possible for calyx 4 arene, but as it goes to calyx 5 arene, 6 arene, there are a large number of conformations possible, as you can understand. Okay. These T-butyl groups all right. These T-butyl groups can be easily removed by transalkylation using aluminum chloride and a solvent such as toluene. Okay. But before that to happen, how we can do that? We selectively functionalize maybe 2. Say I functionalize these 1, 3. How? OR. From OH I functionalize them to OR. So, the corresponding ones can be, I can remove them if I react it with aluminum chloride. If I react it with aluminum chloride, then I can remove them. Okay, let us do it this way, it's big easy. I can remove them, I can make this, so that hydrophobicity, its chemical properties can be modified. OR, OR, I can make this, and then I can replace, then I can add different reagents to that. And for example, E plus will be added, and we can get actually we can replace all of them after that. We can get all of them also. Jesus. We can get all of them, and then yeah, we can put E. Where this E could be, say bromide, nitro. So, we have to do SO3Na. Let me write the one, not make any mistake. SO3Na, then N plus, Me, and so many with other things. What that will happen? That can make this upper also hydrophilic in nature. So, that means we can change, we can do systematically regioselective substitution can be made both at the upper rim as well as at the lower rim, and that will change many that will change its hydrophobic or hydrophilic characters, and we can make different hybrid structures. I will show you some examples of hybrid structures which I have done here, which I have kept here. Okay. So, we can do hybrid structure. For example, I can make a crown ether can be added. Okay. A crown ether can be added. A crown ether can be added. We added a cryptand. We added a cryptand. So, many things can be added. Basically, it means many things may be added to this thing. Okay. Okay. Many things can be added. We made this compound. Systematically, we can change this, not here, but here, and we can put a cryptand like that, or we can put can combine them. Okay. This can be combined, and we can get many different types of structures. So, what is the fascination about fascinating aspects of these structures? These structures can easily exist in different conformations, and when it is in different conformations, their properties can change. And we can exploit that to make molecular machines, because we can systematically make hybrid structures, and that hybrid structure can do some wonders. So, we can do that, number one. Number two is it can accept hydrophobic guests from top and hydrophilic guest from here, that can be modified through upper rim modification. I can make both hydrophilic in nature, and this one is of course always hydrophobic in character. So, this kind of hydrophobicity, hydrophilicity can be played with. Some different hybrid structures can be synthesized, which will do different purposes. So, that gives us an entry into molecular machines, and that can be done at room temperature very easily. So, all these are very, very fascinating aspects of chemistry of these molecules. Okay? Chemistry of these molecules, and as I told you that 4 and 5 are non-planar structures, but as we go higher it can crystallize. When in crystalline form it will form flat also, okay, flat it can form. Now, there is another here, I will just in a passing remark I will tell you, these are arenes, but I can put resorcinol also there. So, there will be resorcarenes. So, different kinds of these basic structures can be played with. I have methylene spacers here shown, but these spacers can be ethylene also. Okay. So, these methylene spacers can be also played with. We can increase this spacer from methylene onwards. So, these things are, these compounds can be varied so many different ways, and that gives us an handle to these materials for use in different structures. So, this is a very good supramolecular synthon and is really a milestone in the development of supramolecular chemistry. Thank you.